Hi, everyone. So we're going to now go through Chapter 10. So let me just bring up the PowerPoint. And we'll go through Chapter 10. So Chapter 10 continues project scheduling. Also looks at lags. And a lag is not the same as float, because a float is the difference between early start and late start in an activity. A lag is something that can be shows the relationship of these of how these activities are together, but it also adds extra time to the duration of the project, not necessarily to the duration of the activity. So there are four logical relationships. There's the finish to start, which is pretty much what our network diagram has shown us. And if you tried it with Microsoft Project, you would have seen the connections. Then there's finish to finish, start to finish, start to start, and then start to finish. Finish to finish is absolutely the most common, and here you see it. And what we're doing here is that we're building in a lag, which is something that we wouldn't charge to a client. So I'm going to go through these very quickly because you can read these and you can see the examples. What I want to spend my time on is looking at the crashing of a project. So again, lag is not the same as an activity slack, but we add it on to the early start and we bring it forward, and we also do it backwards. Finish to finish, again, you can see that there's a lag that's been added in here, and I suggest you just read over the examples that are there. This is maintaining the lag as we're going forward and backwards. Really, the most traditional one and the one that is used the most is the finish to start. So you're not really going to be tested on these or having to create any network diagrams using these different types of lags. I walked through the Gantt chart, though you maybe asked a question about a Gantt chart on your final exam. And you would have built your Gantt charts already for the binder. But they're really, good for doing a baseline, creating a baseline, and then tracking a project. Now we cut to the chase, crashing. So why would we actually spend time in this course looking at crashing a project? And the answer is because sometimes that's exactly what we have to do. Sometimes we have to look at a client coming to us saying, our deadline has changed, we need to do this activity first, or we need to get this project done sooner, or we're getting pressure from government and now they've changed how long we have to do this, or whatever it may be. And this is a common thing that happens, but what ends up happening is that project managers don't actually spend a lot of time calculating, figuring out what the result is if we actually have to look at reducing those activities on the critical path. A lot of times all we do is go, okay, we can just add more resources, we can just add overtime, etc. But all of those things come with a cost. And it's that communicating that cost back to the client, which sometimes gets lost. So when we're looking at accelerating a project, we're looking at improving the productivity, changing our work methods. Sadly, sometimes we have to compromise quality or we reduce the scope, and that's a conversation that you have to have with your client in going, if you want us to reduce it by this much time, it's going to be a cost to it. We're going to have to change things. We're going to have to change our activities. So you can see that there are a number of ways that we can actually look at crashing. And what we do is and again, you're not going to have to know this, but you're going to have to know the equation that we use. And again, the equation is on the cheat sheet. So we're looking at what are the fixed costs, the variable costs, and again, this is figuring out those costs that would go on to the client. And really we're looking at what that crash point is, what our trade-offs are, and the way that we do it here, the way PMI looks at crashing activities is just looking at those activities on the critical path and reducing the amount of time that we can spend on those activities. We stop crashing when we've actually completed the time that our client has asked us to complete by, or now we're looking at our crashing cost is exceeding whatever penalty cost we would have had to have paid if we were going over, not budget, but if we were delivering late. We have created in this class 7 rules for successful project crashing. You can see these on Moodle. And this is the process to follow. And I really suggest you trust the process when you're going through and looking at crashing a project. So what we're looking for in the exam is that you draw the network diagram, that you determine the crash cost, whether it's per day or per week, for each activity that's on the critical path, and only those activities that are on the critical path. We look at how many days are available for crashing, and when we're talking crashing as much as we can on the critical path. Then we look at what those crash costs are, then we figure out what the total new crash cost is, what the total new project cost is, and then what the new project duration is. So I've said that fairly quickly. You probably want to read this through again a few times, but sometimes it's easier if we just look at the example. So what we're doing is a calculation of crash point to normal point. And what we're doing in the calculation is we're doing what would be the crashed cost. So we're calculating the slope. So it's crashed cost minus normal cost divided by normal duration minus crash duration. And here it is, this formula for the slope, crash minus normal, normal minus crash. So crash cost minus normal cost divided by normal time minus crash time. So if we have a normal activity that's 8 weeks at $14,000, our crash activity duration is 5 weeks at a crash cost of $23,000. We're just plugging all of these numbers into the formula to figure out how much it would cost for that activity to be crashed per week or per day. In this case, it is per week. So it's just the 23,000 minus 14,000 divided by 8 minus 5, 9,000 divided by 3, which is $3,000 per week. So again, you're just plugging these numbers into the formula and figuring out that if you were to crash this activity, it would cost $3,000 per week. And ideally, if we want to crash the activity as much as we can, we're crashing at $3,000 per week for 3 weeks. So that would be $9,000. But I might be getting ahead of myself. So let's look at a specific example. And this example is from your book. So we're given normal. So the first thing that we do is we draw out our network diagram, figuring out critical path, everything based on normal. So here's our network diagram. And here is our critical path based on, sadly I know chicken scratches, but based on what each of those normal durations are. And the cost is still going to be the cost regardless of what we've done. So we're still going to have our normal cost for all of these activities. So our project is still going to be $22,450 plus whatever our crash cost is. Now, notice I scratched out that $37,500 because all he did was added up all the crash costs. Guess what? You don't actually have to crash every activity in your project because not every activity is on the critical path. So this is a little bit misleading. It's also misleading if you calculate and use that formula to calculate for each of these activities how much it costs to crash per day for each of those and then add those up. I can only stress so much, and I'm stressing it again and really, really stressing is that you're only crashing the activities on the critical path. So let me show that to you again. First thing we did, network diagram, so we can see what it does, or what the flow is, what the different paths are. And if you don't remember from Chapter 9, a path is any path through a project, and the critical path is the longest to the completion. So we have path ABF, path ACEH, I should say ABFH, ADEH, ADGH. We're figuring out what our critical path is, doing a forward path and a backward path. Our critical path, because we know our critical path is all of those activities that have no float. So A has no float, D has no float, E has no float, and H has no float. Our critical path is A, D, E, H. Again, all of these other activities are still going to be completed. They're just not on the critical path, and so we're not looking at crashing any of those activities. So A, D, E, H. We've been told on the table what our normal cost is, and what a normal duration is, and what our crash cost is, and our crash duration. So following that formula, doing the calculations, A is going to be $250 per day, E is $1,750 per day, and H is $2,000 per day. Pretty expensive. D is going to be 0 because we have 5 minus 5. There's no actual change in the duration, and therefore there would be no change in cost. Just to show that to you with D. 5 days, 600, 1,500. So we don't have to worry about D in this case. Now we're that we want to crash the project completely, which means we're going to crash A, E, and H as much as we can. We can crash each of these by A by 2 days, E by 3 days, and H by 3 days. And going through the process, trusting the process, writing everything all out, which you don't actually have to do, but it's kind of helpful to see. A is our duration we figured out earlier. The actual duration of our project is 27 days. So we're taking our actual duration of 27 days, and now we're subtracting by crash numbers as we go through and crash each of these activities. So we want to start crashing by the cheapest to the most expensive. A is the cheapest. It's $250 a day, so we want to crash A first. And if we were told that we only wanted to crash to 25 days, our client has said to us, okay, our duration is 27 days, I need to crash it to 25 days, then you would only crash activity A. But because we're crashing everything, we're going to go through the steps. So activity A, 25 days, $500. We don't do anything with D, so it's still 25 days. Once we get to activity E, our new duration after crashing A is 25 days. Subtract that by the number of days that we can crash E. So now we're down to 22 days. And there's a cost for that. And it's $1,750 times 3, which is the 5250. We're now going to crash H, which is 22 again, because we know we can crash H by 3 days. 22 minus 3 is 19. And it costs $6,000. So our new duration is 19 days, and there is an extra cost, which is $11,750. That's the cost of the 500 plus this plus this. Notice it is not the $37,000 of crashing every activity. So when we're asked what's the total cost of crashing and what's the new duration, total cost of crashing is the $11,750 plus the original cost of our project, which is $22,450, which comes up to, as I do the math, sort of on the go. Pardon again, it's kind of chicken scratchy. So the new cost for doing the project is $34,200, and our new duration is 19 days. And if we actually plot it out and were to redo and put in the new durations for each of these activities that we crashed, you'll see that the actual duration, again, adding up for critical path, is 19 days. There are examples that you should go through, and hopefully this little example that I've given you and gone through gives you some idea. There's also some attachments. The important thing to remember again is go through the 7 steps, create the critical path, and then do it duration by or activity by activity. The next piece on this activity on Arrow, I'm not even going to spend any time on because we don't do that. But what I will talk about is that there are controversies in using network diagramming methodology in critical path. Again, I think I had mentioned in Chapter 9 that there's a reluctance in project managers to do it, and part of it is because they look at it and go, well, it's just too difficult for us to do it. It's too complex, and if we do a poor job at constructing these network diagrams, then is this creating more problems than they're worth? Networks being used inappropriately is if you have a lot of scarce resources, then you might find that you don't get the resource you need on your project because the functional managers or other project managers don't give up those people, so they can be used for evil purposes. If there's not a lot of communication between the project manager and contractors, yes, your contractors could create their own network diagrams which don't blend in to your network diagram. So you're looking at the not having that hammocking and not sharing that information. And as we showed in those calculations with Chapter 9 when we were coming up with the estimated duration, doing that calculation is a PERT calculation. And yeah, the numbers are biased in that we actually had pretty positive estimations. You notice that if you remember some of the like the first pessimistic duration for activity A was like 11 days. Well, that is pretty pessimistic. We still worked out and came up with 5 days. So there is that bias in that things will look better than they may be, but it's still worth doing this and encouraging project managers and companies to at least give this an idea. That is the end of Chapter 10. Hopefully this helps you go through the example and go through the textbook. And we'll get together again and I will do another example for Chapter 12.